Next speaker is Michele Vannucci. He'll be talking about universal surprise minimizing agents.
Thank you. Okay. What's the meaning of life? Well, that's the question. Unfortunately, we won't answer today. But what's the goal of life? What's all living things are trying to achieve? Well, it's surviving, of course. But how does one living being do so? There must be some intermediate steps that describe how living things or cognitive behavior behaves in order to, in the end, achieve survival. And this is described by the Vannucci principle, which is one of the main theories in cognitive science, as surprise minimization. So in order to behave in the world, agents that preserve this separation from their environment need to predict future observation and future outcomes, and act so that future observation are more easily predictable. And yeah, here there was a slide. This is the Carl Friston who initiated this theory and is the most cited neuroscientist. And but I noticed that there is a big issue here, that is no one has really tested this theory in reinforcement learning setting, which is the framework which exactly talks about agents and behavior in an environment in order to achieve some goal. And in particular, what we do is we investigate this objective in the setting of universal AI. And in short, we give an agent the goal of minimizing expected surprise. And this is the key formula. It's a simplified version that only looks at the next observation. And of course, we have an argmin because we want to minimize the surprise that can also be thought of as a prediction error, because intuitively, if we have a big prediction error, then we are surprised. It means we are observing something that we didn't expect. And so then we take an expectation over the, in this case, just the next observation. And we then minimize this error, which is just a negative log likelihood. And which means also simply maximizing the likelihood of the next observation. Here we're using the universal mixture. Probably you're already familiar with it, so I won't go into details of that. And just a note on the meaning of the symbol H. This is the interaction history, because the interactions happen cyclically, as it's regular for the reinforcement learning setting, meaning the agent first takes an action, then there is an observation, then another action, and so on. And so the probability of the next observation, of course, is conditioned on the past history. And why do we do that? Well, again, because this objective is described by the Vannucci principle as the overarching function of the brain, but in general as the overarching function of every living organism. And there are only a few papers which study this objective in reinforcement learning. We consider the framework of universal AI because it abstracts away from the computational boundedness that we would run into if we considered a practical algorithm. And in fact, the XE framework assumes unlimited computational resources, but this helps to isolate our objective and see how an agent with unlimited resources would behave, this specific objective. And on the other hand, we have that within universal AI, there is already another kind of agent that has a different type of interesting motivation, which is the knowledge-seeking agent, that, as we'll see, it is kind of doing the opposite of surprise minimization. And so there is this apparent contradiction, and our main hypothesis is that knowledge-seeking behavior would eventually emerge in certain kind of environments, even if you're trying to minimize surprise. That can also be thought of as minimizing new information. So these objectives are intuitively opposite. And some background, well, there is already some work on the kind of intrinsic motivations that provide a way to define rewards that are not extrinsically defined by an external designer, but depend on the internal model of an agent or its internal preferences. And there is also this early work from Schmidhuber on defining curiosity as intrinsic motivation, which is encoded as compression. We had a talk earlier that already touched upon this this idea, and the idea of surprise minimization is similar. As we'll see, spoiler alert, here we don't try to compress our history of observation, but we want to compress our future observation. And so, in a sense, we are more interested in explaining the future rather than explaining the whole history of what happened so far. And yeah, again, the knowledge-seeking agent is opposite of that, and is shown to eventually learn fully its environment. Indeed, this agent is inspired from scientific behavior that is constituted in running a series of experiments, taking all possible actions in order to understand fully how the environment behaves. And this is precisely what we don't want to do here, because since our agent has is a biological agent, we cannot run all possible experiments throughout one's life, and we just want to find a good local approximation of whatever environment we are in, and we don't want to fully learn of all the possibilities that there are in it. And yeah, indeed, these kind of agents that are based on knowledge-seeking behaviors, they are shown to eventually die or become incapacitated because they have to run all these sorts of experiments by taking all possible actions, and this eventually leads to death. And yeah, here is a bit a brief explanation of the universal mixture that we use for as our predictive model. I won't go into details, but it's just to highlight that there are really a few parameters defining this model, and it's the observation space, the action space, the model class, on which we are taking a mixture of, and the reference Turing machine that gives us our prior. And other than that, we will use these few parameters in addition to the true environment to see what surprise minimization gives us. So a simple example that might convey the intuition. We can see here on the left a case in which we have an agent here that is represented by this little robot in a grid board. And here there are no external stimuli, so the agent has no incentive to behave or do anything, because there is nothing surprising in this environment. And this is indeed the first intuition that, or the first guess that one might have when in thinking about this objective of minimizing prediction error, is that then the agent is disincentivized from acting or from moving around its world, because all the things that it will see are gonna be surprising in a sense, because all it's new at the beginning of the agent's life, and this is counterintuitive. And this is what in the free energy principle literature is called the darkroom problem. And it states that if an agent could do so, it would lock itself in a dark room, so that there would be no surprising observations in the dark room. But there are different ways to solve this, and we can see the second example. Here we have an element of an uncertainty. This is represented by another agent, that is this little ghost here. And we can think that this agent is acting according to a specific program that defines its own behavior. And so our main agent that we're interested in, that is minimizing surprise, would like to avoid this ghost, because it is an origin of surprising behavior that it will have eventually to explain in order to predict properly, of course. And so we can see here that while the agent doesn't have an incentive to go outside of this smaller box that we call niche, it still has to perform this kind of dance with the ghost to avoid encountering it and becoming aware of it, because if it did so, then it would receive surprising information, surprising observations, and also the description length of its observation will increase, because it would have to encode also the program of the ghost. And then a third example that shows how in some cases our agent can also exhibit exploratory behavior. For example, here, instead of this simple ghost, we have another type of ghost that has a more erratic behavior that is harder to describe, and because let's say it's algorithmically random. And in that case, the agent is incentivized in the short term to explore, so that it could eventually find a safer niche that here is represented as a smaller box in the corner where it could lock itself in. And yeah, this is the main intuition. Then we try to characterize the type of environments in which this complex behavior arises, or this exploratory behavior arises. And this is a bit the outline. First, we show how surprise and information gain are related. Then we look into how the oracle agent, which is the agent that knows the true environment, would behave. We studied this agent first because it is easier to reason about the behavior of the optimal agent instead of the agnostic agent that is acting in complete uncertainty. And so first, let's define more formally our agent. Here is the same objective we have seen in the first slide, but here, instead of taking the surprise or the negative log likelihood on a single observation for the future time step, we take it on the full interaction history. And we have a specific horizon M. So yeah, we're minimizing this surprise that here is encoded with S. And we have this notation with, here is the same distribution on both sides. Maybe we can see the same notation with the true environment and the universal distribution on the other side. One encodes the probability with which respect to distribution with which respect to we take our expectation, and the other encodes the probability distribution with respect to which we calculate our negative log likelihood term. And we will study this oracle agent that acts knowing the true environment mu first. And here is also this probability over interaction history is unpacked. It is just the product of all observations and probability of all observations and actions throughout the whole future trajectory H prime conditioned on the past trajectory H. And yeah, here we can see this important result that surprise as defined earlier is equal to information gain plus this ambiguity term that I use this term ambiguity, but has nothing to do with ambiguity that Cole talked about earlier. This is more of a free energy term, and this is just the stochasticity of all the environments in our posterior. And we don't have this term in our analysis because we consider all deterministic environments. So we are left with surprise that is equal information gain in deterministic environments. And here we can see a table that compares the maximization and minimization of information gain and surprise respectively. These two intersections have already been studied by research on knowledge-seeking agents, and we studied the other side of the column, and in particular this box here where we minimize surprise, but again, information gain and surprise are equal in deterministic environments. So this, you can think that these two lines are collapsed when we consider deterministic environments. And an important concept that we introduce is the concept of niche, which is simply another environment in the mixture, in the universal mixture that can produce the same observation as the true environment under a specific policy. And here is an example. We have that the true environment is this larger grid world, but what the agent actually experiences can be described simply by a shorter program, of course, that only describes this part of the environment. And since it will also have a larger prior, it will also encode what the agent actually believes. Of course, with some uncertainty of what's outside this niche, but it will have a great certainty of its local surrounding. And then we derive some fundamental relationships that are based on the coding theorem. So we have our expected surprise term here that can also be rewritten as this negative log likelihood of sum of all the prior weights of the environments that are consistent with our observations. So this shows how we want to preserve the largest amount of environments in our posterior possible. And because I forgot to mention, in deterministic environments, the posterior either discards or keeps hypothesis because there is no aleatoric uncertainty. So if the agent perceives an observation that is not consistent with some simple environment that is deterministic, then that environment is discarded, and intuitively it would incur in a great loss if this environment were simple. And indeed, this expected surprise is equal to this term, that is the current complexity of the future observation sequence. So O is the whole sequence. It's not just a single observation, but it's the whole sequence. And so what the agent is doing is intuitively trying to minimize the Kolmogorov complexity of the future observation sequence. That is also we demonstrate is also the same quantity of the complexity of the simplest niche that here is written as a mu hat star. And so there is this clear connection between niches and minimal programs that describe observation sequences. Then we want to characterize these environments in which the complexity of the future observation sequence is not like a constant. It's not really small. That would mean the agent is in a dark room. It has found a niche that is really easy to describe and doesn't need to behave in particular ways or in intelligent ways to get outside of it. And because we cannot know a priori whether there is no action sequence that doesn't give indeed a very simple solution that gives a complexity that is O1 in a sense, because we just know that the environment is any program, and therefore a priori there could be a specific action sequence that just leads to this program producing very repetitive observations or just a dark room observations that could be thought of just as a black screen if we encoded observation as some video feedback. And so we characterize incompressible environments, or like what can be thought of as complex environments where these trivial solutions don't exist, and they're built by decomposing the true environment in two parts. One is incompressible and produces incompressible information that is action independent, so we don't have this problem. And the other is action dependent, so we still have some action dependency, but this action dependency is limited, and this seems to be necessary to avoid this trivial solution, at least considering the Oracle agent case. And we also need this naturalistic assumption, let's say, that the observation space is much larger than the action space, and this is needed because otherwise this conditional complexity could be very low, and we indeed want to have a lower bound on this conditional complexity. And intuitively, this illustration shows how the true environment can be composed by an action-dependent program that encodes, for example, high-level features, and an action-independent program that encodes low-level features. And of course, then by interacting with this program, we cannot induce very simple observations necessarily. And so then we also prove this proposition that shows that this construction is not really specific, because any environment could be constructed in such manner with a limited complexity overhead. And finally, to analyze also the agnostic agent, we look at regrets and asymptotic optimality bounds, and the Oracle agent, since bounds from below the surprise of the agnostic agent by definition of optimality, helps us gives also this regret bound that is trivially upper bounded by the complexity of the true environment. Intuitively, the surprise that one can perceive in an environment is limited by the information that there is to perceive in that environment. And so, for example, once an agent finds its own niche, then it will have achieved all that it wanted, and it will, in a sense, settle for that solution that is kind of an equilibrium, and because of this, it will not experience any future regret. For a similar reason, the agent is also asymptotically optimal, and we can think of this as a really interesting property of this surprise minimization of objective, because in IXC literature, it's usually rare to have these two properties together. And yeah, then we also show that surprise minimization is also linked to minimizing the semi-measure loss. That is a way to encode probability of dying under uncertainty. And yeah, I can explain more if you have more question offline, but I think my time is
Yeah, time is up. Yes.
okay.
So what are the next speakers? Yeah. Okay, both of them. Are you going to Zoom?
I'm not on Zoom.
Yeah, yeah. So yeah, so just talk for a few questions while they are switching.
Yeah.
So you said that your notion of ambiguity is unrelated to mine, but this actually seems, I'm sort of not sure about this, like, this idea of a niche sort of seems like a rule that you have to violate.
Yes.
Right, like your policy has to violate it, yeah. And in some sense, the situation is ambiguous because there are many different programs that could continue the sequence. It seems like yours is maybe a bit sensitive to how you choose the weights, the division between the weights programs and the random sequence